Welcome to our chapter on thermodynamics, where we'll dive into the fundamental principles that govern heat, energy, and temperature in the physical world. In this thermal properties can determine how it reacts when it is subjected to excessive heat or heat fluctuations over time. We shall take a look at the following thermal properties such as thermal expansion, thermal conductivity, thermal stress. First is thermal expansion. When the temperature of a material increases, most materials expand. The change in length with temperature for a solid material is called linear expansion. The equation involves the initial length and the changes of the length respected to the temperature changes. For area expansion, the change in area with temperature for a solid material involves the beta-Wich coefficient of area expansion. For volume expansion, the change in volume with temperature for a solid material involves the 3 times alpha-Wich coefficient of volume expansion. All the equation are stated as follows. The property that characterizes the ability of a material to transfer heat is called thermal conductivity. The equation for thermal conductivity is P equals to heat over change of temperature. For each material exhibit different thermal conductivity. Different materials have different thermal conductivities due to variations in their atomic structure, bonding, and the way energy is transferred through them. For example, metals like copper and aluminum have high thermal conductivity because their atomic structure includes free electrons. These electrons can move easily through the material, transferring energy quickly from one atom to another. This makes metals excellent heat conductors. The stress induced in a body as a result of changes in temperature is called thermal stress. The equation for thermal stress is alpha times Young modulus times changes of temperature times area. Matter exists in different phases or states, each with unique properties based on how particles are arranged and interact. Here are the main phases of matter including solids, liquids, and gases. The solid phase of matter has a definite shape and volume. The particles in a solid are tightly packed together and cannot change position easily, they only vibrate. Examples of solid materials are rock, window, desk. The liquid phase of matter has no definite shape, but it has a definite volume. Liquids have no definite shape because the particles in a liquid are able to change position. For examples are water, dish soap, and others. The gas phase of matter has no definite shape or volume. The particles in a gas are always in motion and they can move freely to all parts of a container. For examples are air, oxygen, hydrogen, and others. The next topic is about heat and temperature change. Heat is defined as the transfer of energy across the boundary of a system due to temperature difference. Heat is energy that flows from a higher temperature object to a lower temperature object because of a difference in temperatures. A transfer of energy due to a difference of temperature. C unit of heat is in joule. The temperature is measured using thermometer. It is the measurement of degree of hotness. The units for temperature can be in Kelvin, Celsius, and Fahrenheit. Temperature is a measure of how hot or cold something is. Most materials expand when heated. In this video shows the conversion for the units of temperature. Now we move to the zeroth law of thermodynamics. It is defined as if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. So there will be no energy flows from one to the other, and their temperatures don't change. Before we go into the specific heat, let's understand about heat. Heat is an energy transfer due to differences in a temperature. It flows from hot material to a cold material until thermal equilibrium is achieved. Specific heat capacity is defined as the amount of heat Q required to change the temperature of a given material is proportional to the mass m of the material present and to the temperature change dTt. It can be expressed in the equation Q equals to mass times specific heat capacity times changes of temperature. The table shows the specific heat of each materials are different. The specific heat of a material is different due to several factors related to its atomic and molecular structure, bonding, and the way energy is stored and transferred within the material. Let's go to the example. In a 30 minutes, a 65 kg jogger can generate 8.0x105 J of heat. This heat is removed from the body by a variety of means, including the body's own temperature-regulating mechanisms. If the heat were not removed, how much would the body temperature increase? To solve this problem, need to use equation of heat related to specific heat. So change of temperature is equals to Q over mc. 8.0105 joule over 65 times 3470 the specific heat for human body equals to 3.55 degrees Celsius. In discussing heat and thermodynamics, we shall often refer to particular systems. A calorimeter is a device used to measure the amount of heat involved in a chemical reaction, physical change, or heat capacity of a material. In calorimeter, it is well insulated so that almost no heat is exchanged with the surrounding. When different parts of an isolated system are at different temperatures, heat will flow energy is transferred from the part at higher temperature to the part at lower temperature, that is within the system. If the system is completely isolated, no energy is transferred into or out of it. Therefore, it can be related to the conservation of energy. Heat lost equals to heat gained. Let's go for example. 100 G of metal X initially at 115 degc is dropped into 1 kg of water that is at 25 degc. The final temperature for both substances is 50 degc. Calculate the specific heat capacity of metal X. Specific heat capacity of water 4200 J/kg degc. Heat loss is equal to heat gain, so by using the equation of mc delta theta, the specific heat of the metal can be solved. There are three states of phase which are liquid, solid and gaseous. So the amount of heat that changes substance from a solid to liquid is called heat of fusion, LF. The latent heat of fusion is defined as the amount of heat necessary to convert 1 kg of the solid to 1 kg of the liquid. Meanwhile, the amount of heat that changes substance from liquid to gas is called latent heat of vaporization, LV. The latent of vaporization is defined as the amount of heat that is necessary to convert 1 kg of the liquid to 1 kg of the gas. This graph shows the change of phases ice to water then vapor. In these stages involve heat and also latent heat because involve changes of phases. In thermodynamics, relationships involving heat mechanical work and other aspects of energy and energy transfer. So now let's understand about first law of thermodynamics. It states that if some quantity of heat is supplied to a system capable of doing external work, then the quantity of heat absorbed by the system is equal to the sum of the increase in internal energy of the system and the external work done by the system. Thermodynamic processes describe how a system's state changes due to interactions involving heat, work, and internal energy. These processes are fundamental in understanding how energy is transferred and transformed in physical systems. Here are the main types of thermodynamic processes: isothermal, where temperature is constant; isobaric, where pressure is constant; isovolumetric or isochoric, where volume is constant; and lastly is adiabatic, where no heat transfer. Now we move to the second law of thermodynamics. The second law of thermodynamics is a statement about which processes occur in nature and which do not. There are many ways to state the second law here. As one, heat can flow spontaneously from a hot object to a cold object. It will not flow spontaneously from a cold object to a hot object to a hot object. It is not possible for heat to flow from a colder body to a warmer body without any work having been done to accomplish this flow. Energy will not flow spontaneously from a low-temperature object to a higher-temperature object. The methods of heat transfer are conduction, convection, radiation. The first method, conduction, is heat is transferred directly through a material. Two systems in contact, one at a higher temperature, hence energy transferred from high body temperature to lower body temperature. Factors affecting heat transfer are time, more heat transferred, more time taken, temperature difference, greater difference, more heat transferred, cross-sectional area of body in contact, length of heat transfer. Metal is the best conductor. Secondly is convection process, in which heat is carried from place to place by the bulk movement of a fluid. When part of fluid warmed, volume of fluid expands, density decreases. Warmer fluid pushed up, cooler and denser fluid replaces it. Cooler fluid, then warmed up and pushed up, thus continuous flow established. Third is about radiation. Radiation is the process in which energy is transferred by means of electromagnetic waves. It happens when energy from sun brought to earth by electromagnetic waves. Process does not require medium, can go through vacuum. All bodies continuously radiate energy. Example: human body detected using infrared detecting electronic cameras. Even an ice cube radiates energy. It can be concluded that material that is good absorber is also a good emitter, for example black. A material that is poor absorber is also a poor emitter, for example polished silver. A perfect black body, being a perfect absorber, is also a perfect emitter,